In our last lecture, we discussed about Poisson's equation and Laplace equation. So in this lecture, we are going to continue our discussion by discussing this separation of variables method to solve Laplace equation.
So del squared v is equal to 0. And can you remember, because of the symmetry and because of the given coordinate system, when we are solving this equation, we were able to limit the dimensions into a one dimension. Okay, so when we limited our question because of the symmetry and because of the coordinate system, we were able to limit that into either something like this. So mainly into one dimension, only a one variable system. But in general, when we are dealing with geometry, so it can be a three-dimensional geometry. So in those cases, we might have all three coordinate system in a Cartesian coordinate systems. For example, we might have x, y, and z, all three components. So if we have a situation like that, then how we are going to solve this equation in a three-dimensional system? So to do that, what we are going to do is, we are going to select the potential. We are going to say the potential is a function of all three variables, and we are going to assume that it's this potential, we can state it as a separation of x, separation of y, and separation of z, three functions. So if we have a situation where we have all three coordinates, then da bar squared v over da bar x squared plus da bar squared v over da bar y squared plus da bar squared v over da bar z squared is going to be 0. And we are going to look for solutions that are products of function of each of these x, y, and z. And also we are going to assume that it's each of these function will depend only on one of these coordinates. So we are going to, we will look for solutions that are products of functions and each of these functions we are going to assume it's going to depend only on one of these coordinates. Then we can state that the potential now in potential we have x, y, and z components. So we look for solutions that are products of functions. So we have a function of x times function of y times function of z. Now this is the method of solving Laplace equation using the method of separation of variables. Now here the potential function we have separated that function into three variables. Mainly, we have a variable that is only dependent on x, and another variable, another function that is only dependent on y, and another function that is only dependent on z. Then, so we have our Laplace equation, double squared v over double x squared plus double squared v over double y squared plus double squared v over double z squared is 0. And we are going to use this format of potential here. So we have double squared or double x squared, x of x and y of y and z of z. Again here, double squared or double y squared, x, y, z plus double squared or double z squared, x, y and z is equal to 0. Now, if I consider here, only this capital X function is only dependent on x. Other two functions are not dependent on x. Therefore, we can consider relative to x, y, and z are constants. And we will have double squared x over double x squared. Same here. X and z, we can take those out. Double squared y over double y squared plus here only this is going to be dependent on z. Therefore, x and y double squared z over double z squared is equal to 0. Then I'm going to divide all these both of the sides by x, y, and z. And we will have here 1 over x double squared x over double x squared plus 1 over y double squared y over double y squared plus 1 over z double squared z over double z squared is equal to 0. So if we look here, now x is a variable, x is a function of variable x, and y is a function of variable y, and z is a function of variable z. So this part is only going to be dependent on x, and this part is only going to be dependent on y, and here only going to be dependent on z. So here I have f of x, and this is g of y, and you can say k of z. So only function of x, only function of y, and only function of z. Now, if we look here, in order to these three functions to be 0, now this is only dependent on x, y, and z. So each of these functions have to be constants. So this value should be a constant. I'll say k1 square, and this value also should be a constant k2 square, and this value also should be a constant k3 square. Then we can write k1 squared plus k2 squared plus k3 squared should be 0. Now, the importance of this method of separation of variables is, once we do this method of separation, we have each of these functions only dependent on one variable. Then in that case, these partial differential equations, okay, partial differential equations we can reduce to ordinary differential equations, and then it is little bit easy to solve the equations. Okay, so here this moment we have reduced the partial derivatives into ordinary differential equation. So we have 1 over x. We can write d over d squared x over dx squared is equal to k1 squared 1 over y d squared y over dy squared is equal to k2 squared and 1 over z d squared z over dz squared is equal to k3 squared. So each of these we can solve considering ordinary differential equations. Okay. Now let's try a question. So two infinite grounded metal plates lie parallel to x z plane, one at y is equal to 0 and other at y is equal to 1 as shown in this figure. The left end at x equals 0 is closed off with an infinite stripe insulated from two plates and maintained at a specific potential V naught of y. Find the potential inside this slot. So we need to calculate the potential in between these two metal plates. Now here we have one metal plate and here we have another metal plate and we have a insulated stripe like this here. So what we are going to do here is we are going to use this method of separation of variables, since now here we have this potential is going to be vary with y and also x. So mainly we have two variables that the potential depends on. So let's first write the boundary conditions for this situation. Now it is given that potential is 0, grounded metal plates. So potential at each of these plates is 0. Potential is 0 when y is 0 on this conducting this grounded plate, and again v is 0 when y is a. On this metal plate, potential is 0. So those two are the first two boundary conditions that I'm going to consider. Then also it is given potential at x equals 0, it is closed off with infinite stripe insulated from two plates and it is maintained at specific potential V naught of y. So at x equals 0, so the potential is maintained at V naught of y when x is equal to 0. And we can have another boundary conditions. So here we have a specific potential, but what will happen when x will go to infinity? When x is going to infinity, what will happen to the potential? So here we have a specific potential, but the two grounded metal plates, the potential are 0. Then when x is going to infinity, the potential will reach 0 eventually. So when x is going to infinity, potential will reach 0. So these are the boundary conditions we are going to use. And let's start with Laplace equation. So L square B is equal to 0. And the potential, it is depending on x and y. Therefore, we can write dou bar squared V or dou bar x squared plus dou bar squared V or dou bar y squared is 0. And we are going to select the potential. Potential is a function of x and y. And we are going to assume that it is two functions of x and functions of y. Okay. And then like we derived here, we can write 1 over x dou bar squared x over dou bar x squared plus 1 over y dou bar squared y over dou bar y squared is equal to 0. Okay. So we are using the method of separation of variables. Now, here we have a function that is only dependent on x, and here we have a function that is only dependent on y. Therefore, we can say value here should be a constant. I'll say it is k square, and then value here also should be a constant. Then to be two constants, summation of two constants to be 0. If I have the constant here k square, here should be minus k square. Then it will be 0. So we have a 1. We can reduce this partial differentiation into ordinary differentiation now with only considering one variable x, 1 over x, d squared x over dx squared is equal to k squared, and another ordinary differential equation 1 over y, d squared y over dy squared is equal to minus k squared. Then by solving these two ordinary differential equations, we can obtain the potential variation between these two grounded metal plates. Okay, so now here for an ordinary differential equation like this, the solution is going to be in the form of x of x is equal to a e to the power kx plus b e to the power minus kx. Okay, so we can verify this result. So I'm going to consider dx over dx. So once we differentiate this once, we have a is a constant e to the power kx times k plus b e to the power minus kx minus k. Then again, I'm going to differentiate this. D squared x over dx squared is equal to a e to the power kx. And again here k, and with this k, we will have k squared plus b e to the power minus kx. And with here, I'm going to get another minus k. So we have k squared. So we have here k squared times x of x. So this function here is a solution for this given ordinary differential equation. Like in the same way, for the function y, since we have a constant, negative constant there, the solution is going to be in the form y of y is equal to c sine ky plus d cos ky. Now here we have a solution for the function that is only dependent on x, and for the ordinary differential equations that is only dependent on the y. Then we can write the solution. So we considered the potential is a product of these two functions. Potential of x and y is equal to x of x times y of y. So potential now is equal to, here we have the function here we have the function of x, and here we have the function of y. So function of x, it is a e to the power kx plus b e to the power minus kx, and function of y, it is c sine ky plus d cos ky. Now we have four unknown variables, four unknown constants a, b, c, and d. We need to determine these four constants using boundary conditions. Now, what are the boundary conditions we obtained? Boundary conditions are these four conditions. So I'm going to start with this fourth boundary condition. When x is going to infinity, potential should be 0. So when x is going to infinity, potential needs to be 0. So if I apply, like if I consider this x is going to infinity, then what will happen to each of these terms? This term and to this term. So this term will reach 0, but this term will go into infinity. Therefore, in order to this fourth boundary condition to be satisfied, when x is going to infinity, potential should reach 0, a will be 0. So using the fourth boundary condition, potential is going to 0 as x is going to infinity. When x is going to infinity, this term will reach 0, but this term will not reach 0. Therefore, this constant a will be 0. Okay. Now, this potential, that is a function of x and y, will reduce to b e to the power minus kx times c sine ky plus d cos ky. And here, b is a constant, c is a constant, and d is a constant. So b times c will also be a constant, b times d will also be a constant. Then I can reduce this equation to e to the power minus kx. Now b times c. So I will just use c constant there, sine ky plus b times d is also a constant. So I'm going to use the constant d there, d cos ky. Now, starting from 4 unknown constants, we have reduced up to 2 unknown constants. Okay, is it clear? Any questions up to this point? Any questions or anything? Then we are going to apply these boundary conditions when y is 0, potential is 0. So potential of x and y is 0, it is equal to e to the power minus kx times c sine, now y is 0, plus d cos 0. So this term is going to be 0, but this term we will have d. So we have e to the power minus kx d. And here the potential is 0 when y is equal to 0. Therefore, either this term or this constant d should be 0. And if we consider this one, then all the like potential is going to be vanished. Therefore, only possible situation here is d is equal to 0. Then we can further reduce the potential function. It will be now potential of x and y is equal to e to the power minus kx times c sine k y. Okay. Then let's apply the second boundary condition. When y is equal to a, potential is 0. So potential y is equal to a. Now it is going to be equal to c e to the power minus kx times sine k a. So this potential is 0. Is equal to c times e to the power minus kx sine k a. So we can select this part, sine ka is equal to 0, which means k times a should be multiplications of 5, and n is going from 1 to up to all the values. So with that, we can write here k is equal to n5 over a. Okay. Now with that result, what we are going to get is the potential x and y is equal to c times e to the power minus, so we have now k is n5 over a, n5 over a times x, then here sine n5 over a times y, and n is going from 1 to up to the all the values, n is going to infinity. So if we look here now, potential is depending on, we need to calculate what is this constant c, and n is going from 1 to all the way up, and we have x, then sine n5 y over a. Then we also need to determine what is this constant c here. So now this function we obtained up to now, it is we have a series of values here, n is going from 1 to up to the all the way infinity. Therefore, we need to consider all these n values. Then if we consider about when I consider about the Laplace equation, it is a linear function. Which means if potential V1, V2, V3, all these functions satisfy this Laplace equation, So if all these potentials are satisfying the Laplace equation, so does any linear combination. So if we consider any other linear combination of these potentials, then that is also going to be a solution of this Laplace equation. Okay, so which means now if I have del squared v1 is equal to 0, del squared v2 is equal to 0, and del squared v3 is equal to 0. Likewise, if we have several set of potentials that satisfy this Laplace equation, then if I write a linear combination of these potentials, del squared v, so here alpha 1 is a constant, then del squared v1 plus alpha 2 del squared v2 plus alpha 3 del squared v3. So this is a linear combination of these potentials which satisfy the Laplace equation. Then this linear combination should also satisfy the Laplace equation. So here del squared v is going to be 0. Now we are going to use that information to this situation. We are going to use that information to this situation. We have n is equal to 1, 2, 3, and all the way up. So we have a combination of these potentials. And we know for each n, it satisfies the Laplace equation. Then we are going to write we are going to consider all of these n values. Then when we consider all the n values, we can write the potential v of x and y is equal to, now we have c constant when we only consider one of these n. C is the constant when we consider one of these n's. So for each n value, we have Cn, then we have e to the power minus n5 over ax and sine n5 over ay. Then we need to consider all of these n values. So I'm going to take the combination or the summation of these potential functions. Yeah, n is going from 1 to infinity. Okay, so this is going to be the general solution for the potential that we are looking for. So for this general solution, I'm going to apply the third boundary condition. So the third boundary condition, when x is equal to 0, the potential is V naught of y. So with that, we have n is going from 1 to infinity, Cn e to the power 0 sine n5 a over y. So this is going to reduce to sigma n is equal to 1 to infinity Cn sine n5 y over a. Potential when x is equal to 0. Now if we look here, it is not depending on x, so it satisfies the condition. It is the function of y only. Okay. Now with this, we can try to calculate what are the values for this C of n. So to do that, what we will do is we will multiply both of these sides by sine n prime phi y over a. So here I'm going to get sigma n is equal to 1 to infinity Cn. Now we have sine n phi over ay. Then with this multiplication, we have sine n prime phi y over a. And in this side, we have v naught of y, then sine n prime phi y over a. Then also we are going to integrate this from 0 to a with respect to dy. So here also integrate 0 to a with respect to y. Okay. Then if I consider this whole term, the solution for this integral, it's going to be in the form 0 to a sine n phi y over a sine n prime phi over ay dy. The solution is going to be in the form, it's going to be 0 if n is not equal to n prime. And it is going to be equal to a over 2 if n is equal to n prime. Okay. So with that, we can have now this whole summation with this sigma, we only get a solution other than 0 when n is equal to n prime. If n is not equal to n prime, it's going to be 0. Therefore, now we will have a, from the summation, it will reduce only one n. So Cn a over 2 is going to be equal to integral of 0 to a v naught of y sine n phi over a y dy. Then Cn is equal to 2 over a integration of 0 to a v naught of y sine n phi over a y dy. Now this is the value it's going to be for the Cn. So Cn is the unknown constant, only remaining unknown constant in our potential. Okay. So we will have, now we know the Cn value and the potential. It is V of x and y is equal to Cn e to the power minus n phi over ax sine n phi over a y, and for all the n values, that is from 1 to infinity. So with the boundary condition, here we obtain the value for Cn. So these are the this is the solution for the potential there. And in that, Cn is equal to this value. Okay. Now this is a kind of very complicated, complicated question. So I don't think this kind of complicated questions are going to be in your exam paper, but if there's going to be something like this, then there'll be some simplified like integrations like this will be given, and there'll be several simplifications. Now, we took a lot of time to solve this example. We have two grounded metal plates, which means at each of these metal plate potential is 0. One of these plate is at y is equal to 0, and other plate is at y is equal to 1, as shown in this figure. And for these two grounded metal plates at y is equal to 0, at x is equal to 0, it is closed off with infinite stripe insulated from two plates, and it is maintained at a specific potential y naught is equal to v naught of y. So this is the specific potential, and it is asked to find the potential inside these two grounded metal plates. So we started with Laplace equation, and since in here the potential is dependent on x and y, we selected, so it will reduce to a 2D problem. And in 2D, we will have dou bar squared v over dou bar x squared plus dou bar squared v over dou bar y squared is equal to 0. And we wrote the boundary conditions. So at the first metal plate, potential is 0. At the second metal plate, potential is 0. And there is an insulated plate at x is equal to 0. And it is maintained at this specific potential. And also we have only the potential here at x is equal to 0. And then once the x is going to infinity, the majority influence for the potential will be from these two grounded plates. So when x is going to infinity, potential should reach 0. Then we use this method of separation of variables. So since it is a 2D problem now, potential x and y should be, we should be able to write it as a function of x and function of y and the product of these two functions. Then we reduce this product of functions into, so up to here it is a partial differential equation problem. Then we reduce that into ordinary differential equation problem. So we'll have this term should be a constant and this term should be a constant in order to this summation of these two to be 0. So we have C1, in my case, I considered k squared. So one of these constants have to be positive and the other should be negative. And then we have two ordinary differential equations, and the solution for this term, for the positive term, will be in this form, and for the negative term will be in this term. Then we wrote a general solution for the potential like x and product of x and y. Then we applied the boundary conditions. First condition, like we use the fourth boundary condition first. So when x is going to infinity, potential will reach 0. Then, so when x is going to infinity, this term will reach 0, but this term will not reach 0. Therefore, a should be 0. Then this term is eliminated. Then potential is reduced up to this format. And we applied the first boundary condition. When y is equal to 0, potential is 0. So when y is 0, this term will be 0, but this term will not be 0. Therefore, in order to satisfy this boundary condition, d should be 0. After that, the potential function reduced up to this format. Then we applied the second boundary condition. For the second grounded metal plate, it is potential 0. So potential is 0 at y is equal to 1. So with that one, we obtained value for k. So k is equal to n5 over a. And then we wrote now he up to here. After this point, we observe the potential is going to be it is going to be dependent on n, and n is going from 1 to up to all the way infinity, and it's not going to be equal to 0, because if we consider potential n to be 0, then all the potential is going to be all this geometry is going to be vanish. So n will only go from 1 to infinity. So we can write a general solution considering the fact that Laplace equation is a linear Laplace equation is linear. So which means if each of these potentials V1, V2, and V3 satisfies this Laplace equation, so does any linear combination. So we using that fact, we can write a general solution for the potential. So we need to consider all the combinations for n. N is going from 1 to infinity, and we have e to the power minus n5 over ax times phi n5 y over a, and we have Cn. Then we applied the third boundary condition at x is equal to 0, the potential will be V naught of y. So with that boundary condition, we obtain a value for Cn. So Cn, so it is going to be in this format, and with Cn and with this equation, we obtain general solution for the potential. It's going to be the final answer for this question. Okay. So we only went through one question today. Now, any problems or anything that you need further clarification?